perceiving dark energy. Kutao. I. Dark energy. The theory of the Big Bang explains how our universe came into existence 13.8 billion years ago. Scientists thought that the expansion might be slowing down due to the attractive force of gravity over time. However, Edwin Hubble's observations in the 1920s and 1930s show that the lights from distant galaxies are red-shifted. The lights are stretched, appearing red. If the galaxies are slowing down, the Doppler effect would make the light less red or blue if the galaxies are moving toward us. Thus, the galaxies are moving away, causing a redshift in the light coming from them. It is similar to hearing the sound of a high-speed train approaching us, passing us, and then going away from us. Due to the Doppler effect, the sound of an oncoming train is different from a train moving away. The approaching train's sound wave is compacted, while the sound wave of the train moving away stretches. Therefore, a redshift in the light wave shows the galaxies moving away from us, rather than slowing down due to gravity as we thought. The expansion in the universe appears to be speeding up. In the late 1980s, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence National Laboratory, began searching for Type Ia supernovas. Then, in the mid to 1990s, the High Z supernova search, led by Brian Schmidt of the Australian National University and Adam Rees of the Space Telescope Science Institute, also began searching for Type Ia supernovas. The two teams of astronomers were using Type Ia supernovas as standard candles to see into the depth and dark distances of the universe. A Type Ia supernova occurs in a binary system where one star is a white dwarf. The other star can be another type. These white dwarfs, with their slow rotation rate, are limited to 1.44 solar masses, referred to as the Chandrasekhar mass. Once a white dwarf reaches the Chandrasekhar mass, it sometimes reignites and triggers a supernova explosion that shines as bright as 10 billion suns. This brightness allows astronomers to see into the darkness of space and the deep history of cosmological time. The two teams' purpose is to measure the Doppler shift of these standard candles of our universe. They wanted to determine if the lights coming from the Type Ia supernovas were blue or red-shifted. The Type Ia supernova studies allow for a deeper and farther observation into space and time. The brightness of the supernovas allowed them to see into the deep and dark universe to determine if our universe was contracting, slowing down, or expanding. The two teams presented their findings in January and then in February of 1998. Both teams discovered that the Type Ia supernovas they observed are redshifted. The stretched wavelengths of the lights from the Type Ia supernovas mean that our universe is not only expanding, but the expansion is accelerating. Astronomers explained the acceleration by the cosmological constant included by Albert Einstein in general relativity field equations or some yet unknown anti-gravitation force. From the Type Ia supernova studies, our universe's expansion is accelerating. Expanding universe. Later that year, cosmologist Michael Turner coined dark energy to describe the mysterious force causing our universe to accelerate. 1. As the universe expands, dark energy maintains a constant push, causing the universe to accelerate even faster. Thus, dark energy is constant as the universe expands. Therefore, the energy must grow with the expanding universe to maintain an accelerating push. Dark energy violates Julius Robert Mayer's 1842 first law of thermodynamics, commonly referred to as the law of conservation of energy, that energy is neither created nor destroyed. In the last couple of decades, many studies have tried to measure the speed of the expansion. The studies have come up with an expansion rate of 67 to 77 kps NPC, kilometer per second per megaparsec. A megaparsec is equal to 3.26 million light-years. So for 2 points in space that are a megaparsec apart, they move away from each other at 67 to 77 kilometers per second. 2. The existence of dark energy is for a current explanation of an event in the universe. We have yet to know what it is and measure its existence. At this time, Dark energy helps explain our universe's accelerating expansion. However, dark energy is dark because it cannot be seen, detected, or clearly explained currently, and it may not even exist in the form we thought. Still, dark energy helps explain the universe's accelerating expansion because it takes energy create the expansion. 2. Our perceptions of the universe. Imagination is more important than knowledge. For knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution. Albert Einstein. Due to gravity's influence, we have a sense of up or down here on Earth. However, there is no up or down in the universe out there. The universe simply goes in all directions. We know up or down here on Earth because we stand on the surface of a massive object that curves space-time inward. If we throw an apple into the air, it will fall back due to the inward space-time curvature. Our perceptions of our universe depend on our understanding of universal laws. However, we also project our conditioned beliefs on Earth onto our perceptions of the universe. Once, we believed we were at the center of the universe and that the moon, sun, and stars revolved around us. Our spiritual beliefs and observations of the universe seem to agree because when we look up into the sky, the moon, the sun, and the stars appear to cross the sky, moving around us. However, from our past experiences, what we see in the universe may not be what goes on out there. Thus, we need a better understanding for a better perception to see our universe more accurately. Let us complete an exercise in perception from different angles and dimensions. We will look at the same objective from different angles and spatial dimensions. A vertical line is a one-dimensional side view of a circle. A circle is a two-dimensional view of a sphere. A sphere is a three-dimensional view of the short axis of an ellipsoid. In 2 dimensions, the ellipsoid becomes an ellipse. We see a one-dimensional horizontal line when viewing the 2-dimensional ellipse from the top. Thus, the horizontal and vertical lines are different spatial views of the same ellipsoid. Depending on which dimensions or angle we view an object, we will see a completely different shape. Yet, all the different views are of the same shape, but what we look at becomes different because our perceptions depend on the angle and spatial dimensions we use for our observation. Our accelerating universe has to do with our understanding of gravity. Sir Isaac Newton first conceived the idea of gravity and its laws, allowing us to understand our universe better. The birth of gravity. There's a legend that an apple landed on Isaac Newton's head that awoke him to the forces of gravity. However, what is closer to the truth is that he probably saw an apple falling from a tree, and what hit upon his head was the moment's epiphany. The apple hitting Isaac Newton on the head is a metaphor for the epiphany that hit his mind, that the apple was falling due to gravity. When we throw an apple into the air, it falls back to Earth due to gravity's attractive force, which is what Sir Isaac Newton realized. With the aid of Henry Cavendish, Sir Isaac Newton worked out a mathematical formula for the force of gravity. Other astronomers came along and used Newton's understanding of gravity to validate the movements of the planets in our solar system. Isaac Newton can explain the attractive nature of gravity and how objects are attracted to each other, but he could not explain how it works. Later in his theory of general relativity, Albert Einstein explained how gravity works. IV. A more fundamental understanding of gravity. In 1916, Albert Einstein published his general theory of relativity, showing space-time curves for massive objects. Thus, Albert Einstein would prove that the apple fell back to Earth because of the space-time curvature created by the mass of the Earth. The apple is accelerating down the Earth's three-dimensional space-time curvature. In Albert Einstein's famous thought experiment inspired by seeing a window washer, he imaged what if the worker were to fall. The worker would not experience weight while falling because there is no attachment to the ground. He would feel weightlessness like in space.